So here's a guided walkthrough of the experiment for the oxidation of Borneol to camphor. A description of how to perform every single step is provided along with separate videos that show each step individually. And if you look at the description in those videos, it has a word text for how to perform each step. But this is to give you a bird's eye conceptual view of what you would be doing in this experiment. There are two parts to this experiment. The first part is the reaction itself, and that will turn Borneol into camphor. It will oxidize Borneol into camphor. Once you have the camphor, though, it's going to be mixed in with a bunch of other stuff, a bunch of other waste for this experiment. And so the second part of the experiment will be purifying the camphor from the waste. But first, the reaction. So in this reaction, you're going to need a hot plate, and you'll also need a utility clamp. I have a separate video for the utility clamp. There are several different nuts on the utility clamp that you can adjust, and that controls how it attaches to the metal rod in the back, or how long it sticks out, or how tightly it's clamping onto something. For this, we need the utility clamp to keep this round bottom flask standing up. So the round bottom flask, of course, has a round bottom and would otherwise roll over. Inside of the round bottom flask, to stir our mixture, we're going to use a magnetic stir bar. So we're not going to heat up our reaction at all in this experiment. The hot plate is not used to heat anything up in this experiment. It's used to stir stuff. There are two knobs on the hot plate, one for stirring, one for heating. Underneath the white top of this hot plate, there is a sort of bar magnet underneath it. And when you turn on the stirring function, the bar magnet rotates. Well, this little pill-looking thing, which is itself a little magnet, is going to line up with the bar magnet underneath the hot plate, and as the bar magnet underneath the hot plate rotates, the magnetic stir bar will rotate too, and that'll stir our solution. So the first thing we need is our first reagent, the molecule that we're going to oxidize, and that is Borneol. So we're going to add 0.5 grams, or half of a gram of that. When you weigh something out, you'll first put a weighing boat on the balance. Make sure that the doors or the windows of the balance are closed, because the currents of air can change, and the balance is sensitive enough where the mass will change as different currents of air brush over the balance. So make sure you close those windows to get an accurate reading. You don't actually care about the mass of the weighing boat that's on the balance. What you really care about is the mass of the chemical you're going to put in it. And so to sort of ignore the mass of the weighing boat, you do what's called tairing. You can see we're pressing that button, which it has a sort of 0/T. When you press that, it ignores anything that's on the balance and sets the mass to 0. So you tare the balance to ignore the mass of the weighing boat. So I'm going to add Borneol here, which is in this container. You'll see that the Borneol sticks a lot to the scupula that we have. And that's because this Borneol was a little old. And so if you leave these reagent containers open, the moisture in the air will get into the container, and the molecules, the solids in them, will start to clump. So if you had fresh Borneol, it wouldn't be clumping like this. Because it's clumping, it's sticking to the scupula, and as you can see here, I have to sort of dump everything on the scupula out by flipping the scupula over. But in general, you wouldn't want to do that. A common mistake I'll see when students measure out solids is they'll take a huge scoop on their scupula, and they'll go into the balance and they'll just dump it all into the balance all at once. And oftentimes that'll give them a mass that's much higher than what they want. So to control how much solid you add to the weighing boat, what you really want to do is take a scoop of solid onto your scupula, bring it over the weighing boat, and instead of flipping it over, shake it just a little bit until some of the solid falls off of the scupula into the weighing boat. And that gives you much more control of how much mass you're adding. You'll see me doing that in another example here, just because this is so clumpy and so wet. You can see the clumps in the weighing boat. I had to turn the scupula over. When you add a solid to a reaction flask and you use a funnel, make sure you use a powder funnel. A powder funnel is different from other funnels because the stem of the funnel here is wider. And so if you use a funnel with a thinner stem, the solid will get stuck in the stem instead of adding to your flask. Also, A mistake I'll often see when students transfer things from a weighing boat is they'll try to scoop it out of the weighing boat, maybe with a scupula, which is very time consuming and you lose a lot of solid. Instead, these weighing boats are made to be bendable so that you can make one of the corners a sort of spout. So you bend the weighing boat in half and then you can pour it, and that gets pretty much all the solid in the flask. So that Borneol is one of our reactants, but as you saw, it's in a solid, which means that all of the Borneol molecules are sticking to each other. But we need them to be free, moving around, so that they're open to attack by the oxidizing agent we're going to add. So we need to dissolve that solid so that those molecules of Borneol separate from each other. And that's what the ethyl acetate is doing in this reaction. The ethyl acetate is the solvent. It's not going to participate in the reaction itself. It's sort of the air that things move through. It gives things space so that they can attack or be attacked. So that's what the ethyl acetate is doing. There are a lot of clear liquids in the organic chemistry laboratory. They all have different safety considerations. And so anytime you get some clear liquid from the stock fume hood, you want to make sure that you put a piece of tape onto the flask that you're pouring the liquid into, and that you label it. As the different flasks accumulate, all of the clear liquids will start to look the same, and it's very easy to lose track of them and then to expose yourself to something dangerous. So you'll label the flask, you'll bring the flask, a short stem funnel, and a piece of parafilm to the stock fume hood. You'll pour in some ethyl acetate. You'll remove the short stem funnel, and then you don't just want to walk this back to your fume hood where you're doing your experiment, because all liquids are always evaporating, and that's especially true of organic liquids. They evaporate really, really easily, but all liquids are always evaporating, and so if you just carried this through the room, there would be vapors of ethyl acetate in the room that you would eventually breathe in. And almost everything in the organic laboratory is toxic in some way. So to prevent you from breathing in any of these vapors as you carry this through the room, you use what's essentially industrial strength saran wrap, and that's called parafilm. So you take off the wax backing of it, and this sticks better to a container when you stretch it a little bit. Then put it on top and press it around the neck of that heirloom air flask. Then you can take that and the short stem funnel back to your fume hood. And we're going to use something to measure out the exact amount of liquid we need. We're going to use something called a graduated cylinder. Gradus in Latin just means step. So if you do something gradually, you do it step by step. When you graduate, you're taking a step in life. And this is a graduated cylinder because it's a cylinder that has, you can see the lines here are all steps. Each step corresponds to a specific amount of liquid. So you can use these graduated cylinders to measure out specific amounts of liquids when you need them. When you attach a bulb to a Pasteur pipette, like you can see here, push down on this thick part of the bulb. That's where you want to put your fingers and push it down into this. If you don't do that, it can be a little hard to get that to attach. So when you're ready to measure this out, you'll of course remove the parafilm. You don't want to destroy the parafilm because you're going to seal it back up once you're done using the ethyl acetate. So you're just removing it from the neck. And then when you pipette something, as far as good technique goes, the first thing you want to do is always squeeze the pipette bulb before you put the pipette tip into the liquid. If you put the pipette into the liquid first and then squeeze, which is a very common mistake for beginning students, it'll squirt out air, which will cause bubbles, and it'll splatter the liquid. So a good technique is you squeeze that first, then you put it in the liquid and draw it up. In general, when you transfer from a liquid from one container to another using a Pasteur pipette like this, you want to try to keep the two containers as close as possible to each other. The further they are, the more chance that some liquid will dribble out of the Pasteur pipette as you carry it across. When you measure the amount of liquid in the graduated cylinder, though, you want to make sure that the cylinder is standing on a level surface. So you don't want to hold that in the air when you check the volume of the liquid in the graduated cylinder. You want to leave it on a flat surface. You want to get eye level with the top of the liquid. When you do that, you'll notice that the liquid is not a straight line, but it sort of bows into a U. That's called a meniscus, and when you read the volume of liquid, you want to read volume of liquid based on the bottom of the U, or the bottom of the meniscus. When you're done using a solvent, always cover it up, especially in the organic lab. It'll evaporate really fast, and so you won't have it available later in the experiment if you don't do that. Also, we're doing this underneath a fume hood, which is essentially a big box with a vacuum cleaner on top that's constantly sucking up air. As it sucks up the air, it makes things evaporate more quickly also. Notice the stem of this funnel, which is used for a liquid, the short stem funnel, is thinner than the one we used to add the solid to the reaction flask. So that's our solvent, ethyl acetate, dissolving the Borneol. Once we have that there, we can start stirring this. That'll help it dissolve better. So you'll turn the hot plate on, and then notice there are two knobs in the front of the hot plate. The one on the left is for stirring, the one on the right is for heating. We're not going to use the heating at all in this experiment, so you'll just use the stirring. That'll make that bar magnet underneath the hot plate start spinning. That'll make the little magnetic stir bar we put in our flask spin with it, and that'll mix our solution. Okay, so the stage is set, and now we just need to add the oxidizing agent. The oxidizing agent we're going to use in this experiment is something called Oxone. It's oftentimes added to pools. That's its most common use. In the organic chemistry lecture class, or on standardized tests, the most common oxidizing agent you would see would be chromium oxidizing reagents, something like sodium dichromate in water and sulfuric acid. Sodium dichromate, the formula is Na2Cr2O7. Chromium is a very beautiful molecule. Indeed, potassium dichromate makes the orange color in some of the pigments that Picasso, or it's not Picasso, that Van Gogh used, excuse me. But we're not using chromium reagents in this experiment because they're extremely, extremely toxic. So this is a slightly greener, safer alternative, although oxone is itself a toxic thing that you don't really want to come into contact with, so make sure you are wearing gloves and you don't get this on your skin and you work with it a little carefully. So we're going to measure out 1.2 grams of oxone. It's a white solid just like before. So you put the weighing boat on the flask, you tear the weighing boat. Now we're ready to measure it out. Our scupula is dirty from the Borneol, so we clean it off with a damp paper towel and make sure you dry it with a dry paper towel. And so now we have our oxone. So you take a scoop of it, and notice as I'm getting close to the amount, instead of dumping it, I'm putting it over and shaking the scupula so that it sort of rains down in a more controlled way. Notice we're using a powder funnel with a thick neck. We're bending the weighing boat so that it turns into a sort of spout. The mechanism for the reaction is provided in a separate video. You'll see in that mechanism, which has 5 steps, that you need not just the oxone, but you also need sodium chloride and water. So we're going to add some sodium chloride. This is just table salt. And the method for adding a solid is always put the weighing boat on the balance, tear it, clean your scupula, and notice how I'm shaking it. I'm not dumping it over. Use a powder funnel. Bend the weighing boat into a spout, pour it in. Now we just have to add the 1 milliliter of water needed for the reaction. And again, why do you need water and sodium chloride? That's explained in the mechanism video that I also have posted for this. So 1 milliliter of deionized water. Notice the stem of this funnel is thinner. And then you'll just let that react for 50 minutes. Make sure you're stirring it that whole time. You want to stir it vigorously, but not so much that it's splattering everywhere. After around 50 minutes, we're going to add just a little bit more sodium chloride. Just make sure the reaction goes to completion. Procedure is the same. Weighing boat on the balance, tear it, shake out just a tiny amount of your solid. Powder funnel, bend the weighing boat so that a corner becomes a spout, pour it into the funnel. One error I will sometimes see with students with this is they will lower the stem of the funnel all the way into their reaction mixture. Of course, you never want to do that. You can contaminate your reaction mixture, and also some of it is going to stick to the powder funnel, so you'll lower your yield. So you want to hold that in the neck there. You also never want to leave a funnel in the neck of a container unless you're holding it. Funnels are notorious for flying out of or falling off of containers. So you want to make sure that if you're ever using a funnel, you're holding it. Okay, so we add that extra salt and you let that react for another 10 minutes. So an hour has gone by of reacting with this stirring. Okay, some of the reaction mixture is going to evaporate in that time, and as you'll see in the next purification step, you're just going to need to add a little bit more water, so 7.5 milliliters of water. There are deionized squirt bottles in our lab that you can use for this. So you'll fill up the graduated cylinder. You can use a short stem funnel and then just pour that straight in. And that's the reaction. At this point in that round bottom flask, you have camphor. We poured the Borneol in there first, but at this point it has turned into camphor. The only reason the reaction isn't done, or rather the experiment isn't done, is because there's a bunch of other stuff in there too. There's some extra oxone that did the oxidation. There's sodium chloride, and there's water. And we just want the camphor. So we have to purify it. And that's going to be the second part of the experiment. In the purification, the first thing we have to do is we have to destroy the extra oxone. So we added some extra oxone to make sure all of the Borneol turned into camphor. But now we have extra oxone in there. Oxone is a dangerous chemical, so we want to quench that. And we're going to do that by adding sodium bisulfite. That's the purpose of this. So we're going to add 1/4 gram of sodium bisulfite. The procedure is the same. Anytime you add a solid, put a weighing boat on the balance, tear the balance, and then make sure you have a clean scupula and add that to the weighing boat. Notice how I'm not just dumping that over, but I'm holding it above and shaking it so that I can get a more precise mass. It's almost impossible to get the exact mass that is recommended in a procedure. So the important thing is to get close, and then to make sure you keep a good record of exactly how much you've added. And then if something goes wrong in the experiment, you can always look back at that record to see if maybe that was the cause. Anytime you add a solid, you use a powder funnel, bend the weighing boat so that a corner becomes a spout, pour it through the funnel. Okay, so now that the oxone is destroyed and the reaction is safer, we're going to extract camphor from the reaction mixture. An extraction is where you separate things based on their solubilities. Not all liquids mix. Water and oil don't mix, for example. And things in a liquid will prefer one liquid to another. So, for example, if you had water and oil and you sprinkled some table salt in it, all the table salt is going to go into the water. It's not going to go in the oil. And if you shake it up, it will stay in the water. If you put table salt in oil and then you pour water in that and you shake it up, all the salt is going to go into the water. So the things that are dissolved in a liquid will prefer different liquids. Camphor prefers ethyl acetate to water. It will dissolve better in ethyl acetate than in water. So the way we're going to get our camphor out of that watery reaction mixture is we're going to shake that mixture up with some ethyl acetate. And the camphor will move from the water into the ethyl acetate. So we're going to have to transfer our solution into a centrifuge tube. We're going to use 2 of them, and so you want to label them. And these centrifuge tubes are a lot like test tubes, but the difference is that the very bottom of them is pointed, and that's important for this extraction we're going to do, as you'll see. So we're going to take our pipette and we're going to pipette the reaction mixture into the centrifuge tube labeled 1. Just the whole thing. There's still going to be some stuff dissolved in our round bottom flask, so to try to get as much as we can and clean that out, you'll add a little ethyl acetate to the round bottom flask and swirl it. And that's just trying to get all the extra stuff in that flask out of it and into the centrifuge tube. So you can remove that round bottom flask, shake that up. you want to try to get as much to dissolve as you can. I have a magnetic stir bar retriever here. That's just a wand with a magnet at the end, and you can see that will pull the magnetic stir bar out of the reaction flask. So now you have your funnel, swirl, pour, trying to get everything you can out of that reaction flask. So now we do the extraction. In this test tube, there's the watery solution from the round bottom flask, and now there's the ethyl acetate we just used to clean out the flask. And the camphor is going to want to dissolve in that ethyl acetate, which will be a separate layer. Both ethyl acetate and water are clear, so it's a little difficult to see the two layers, but if you can see them in the lab. When you do this extraction, you want to make sure you close the centrifuge tube, and then you shake the liquids up. That helps the water to mix with the ethyl acetate. Anywhere where camphor is will switch from being in the water to being in the ethyl acetate. As you shake these liquids up, though, they'll oftentimes evaporate a little bit, and pressure will build up in the container. So it's important that you open the lid every 30 seconds or so in order to release that pressure. If you don't open the lid when you do an extraction, the pressure can build up to the point where the container just bursts. So now all the camphor will have gone into the ethyl acetate. It won't be in the water anymore, and it's just a matter of mechanically separating the water from the ethyl acetate layer. So the ethyl acetate with the camphor product that we want is going to be on top. It's less dense. The water solution with all the waste is going to be on the bottom. It's more dense. And this is where the pointed tip of the centrifuge tube becomes significant. So you'll take a Pasteur pipette. Notice the tip of this Pasteur pipette is really long. So this is a 9-inch Pasteur pipette, whereas up until now you've been using a 5 3/4 inch Pasteur pipette. You'll attach the bulb to it, and what you'll do you see the two layers there? The top layer is the ethyl acetate that has camphor in it, and the bottom layer is all the water with all of the junk that we put in it, sodium bisulfite and salt, etc. So we just want the top layer, so we're going to remove the bottom layer. You'll squeeze the pipette and put it all the way at the bottom where the tip is of the centrifuge tube. This is why we're not just using a test tube, we're using a centrifuge tube, so we can really control how we get the bottom layer out of this. We want the bottom layer removed, but not the top layer. So you'll take that up and then squirt that into your second centrifuge tube. And you'll keep doing this until the only thing that's left is that top ethyl acetate layer that has the camphor that you want. One tip is that as you get close, as the two layers get close and you get close to wanting to stop, you don't want to transfer the top layer. You want that to stay in there. And it can get a little tricky to just remove the bottom layer and not the top. One way you can control and make sure you only get the bottom layer there is by pressing the tip, not pushing the tip, because these tips of these Pasteur pipettes can break very easily, but just pressing it gently against the bottom. When the Pasteur pipette is pressed against the bottom of a container, the liquid goes up into it much more slowly, and so you can control when you stop taking things up better that way. And there, the water is removed, and you just have the ethyl acetate. Now, technically, most of the camphor will be in that ethyl acetate solution, but there's still going to be some extra camphor still dissolved in the water. Camphor does dissolve in water a tiny, tiny bit, and so it will still be there. So just to really grab that out, we're going to extract it again with ethyl acetate. Same procedure as the first extraction. So we're going to measure some ethyl acetate out. Notice that I'm squeezing that pipette bulb before I put it into the liquid so that when I put it in the liquid it doesn't splatter. And now we're going to pour that ethyl acetate into our water. Close it so we have our two layers. You can see that line here. Ethyl acetate on top, water on the bottom. Close it. Now we're going to shake it up. Any camphor that was in the water is going to move into the ethyl acetate. Don't forget to open the top of this every 30 seconds or so to make sure that the pressure that builds up inside doesn't make the container explode. So you're venting that. Okay, and now again, all the camphor that was in the water should be in the ethyl acetate, and we just have to separate them mechanically. And we're going to do it the exact same way as before. The water is now going to just be waste. We've really taken all the camphor out of that. So we're just going to put it in a 250 milliliter beaker, which is just a waste beaker. Notice, you really want to squeeze the pipette bowl before you put this in, because if you get bubbles here, it's going to disrupt the separation between your two layers. So as those two layers get close, make sure you're putting the tip at the very bottom so you can control exactly how much you have. If you feel like you can't get all of the water in, you can leave a tiny, tiny bit in. You really want to keep the ethyl acetate in there. You can leave a tiny, tiny bit of water in because we're going to dry the solution twice. So we'll combine the two camphor ethyl acetate solutions just by pipetting one into the other. So both of these just have the ethyl acetate with camphor in them, and you just combine them. And now we want to dry that solution. We're going to dry it in two ways. The first way is we're going to mix saturated aqueous sodium chloride in with the solution. The term aqueous just means that something is dissolved in water. This comes from the same root as aquatic or aquarium. So a saturated aqueous sodium chloride solution is a solution that has salt dissolved in it, table salt, which is sodium chloride. And it's dissolved so much that it can't dissolve anymore. It's saturated with table salt. You can recognize these solutions because they'll often have a blanket of table salt at the bottom of the water. So it's as salty as water could possibly be. It might seem a little strange to dry something by adding a watery solution to it. But the point of this is that wherever salt is, or wherever a solute is, the solvent, in this case water, will go towards it. So water follows salt. Water will follow a solute. It's the principle behind a lot of diseases that involve swelling in places where liquids build up in a body. It happens because the water in the body is following a solute. Oftentimes it's salt. One of the reasons for high blood pressure, if you have a lot of salt in your diet, you get a lot of salt in your blood, and then the water follows that salt, the water in your tissues follows that, goes into your arteries, and then your arteries swell until they, for example, burst. So we're going to use that idea to dry the solution, because when we shake this really, really salty solution up, all the water is going to go towards it. Water follows salt. So we'll pour this salty solution in, and any water that was left over in your centrifuge tube is going to go towards the salt and separate into that separate layer, which will be the bottom layer. So we do another extraction. Notice I vented it after 30 seconds or so, and then we want to separate our now dry camphor ethyl acetate layer, which will be the top layer, from that saturated aqueous sodium chloride water layer on the bottom. And we're just going to do that mechanically, just like we've done before. Notice you're using 9-inch Pasteur pipettes with these centrifuge tubes because they're so long. The centrifuge tubes are so long. Make sure to squeeze the pipette bowl before you put it in. The last drying procedure that we're going to use is anhydrous sodium sulfate. There are a lot of different salts that just absorb water. For example, a lot of things just will absorb the moisture in the air. Even at the beginning of the experiment, you saw how the Borneol clumped because it absorbed water in the air. And you can use that to dry things. You can use that property to dry things. So in this case, we're going to dry the solution with sodium sulfate, which is a type of inert salt. It's not going to react with anything. But the point is that it will absorb water. Before sodium sulfate has absorbed any moisture, it's called anhydrous. Oftentimes they'll take the sodium sulfate and they'll heat it up so any water boils away. That'll make it anhydrous. You can see the word hyd here, and that's referring to water, like if you're hydrated, you're drinking water. The prefix a or an in Greek means not. So if something's not typical, it's atypical. And here, because this starts with something that sounds like a vowel, they add the n. So anhydrous just means there's no water on this, and that means it's going to be able to soak up a lot of water. So we'll take a heaping scoop of sodium sulfate. So you'll pour your mixture of the ethyl acetate with camphor into a beaker where it's easy to scoop some anhydrous sodium sulfate, and we'll take a heaping scoop. A heaping scoop is a scoop that goes above the level of the container that's holding it. That's what it means to be heaping. So you'll just pour that in. You'll know you've added enough sodium sulfate because there will be some sodium sulfate that does not clump. When sodium sulfate is all wet, it's clumped. So if there's some that isn't clumped, then that means all the water's been soaked up. The solvent, ethyl acetate, will evaporate very, very quickly, and so you want to make sure you cover that so that it does not. You don't want the solution to dry while you still have the sodium sulfate there, because then you won't be able to take your solid camphor, you won't be able to distinguish it between it and the sodium sulfate. If that does happen to you, just add more ethyl acetate. It will dissolve the camphor, it won't dissolve the sodium sulfate. And you'd let that sit for 10 minutes. Now after that's dried, for our lab, you're in a position to run an IR spectrum. So you can take a pipette, a Pasteur pipette with a bulb attached, and put a drop of this on the top of an IR spectrometer and see what functional groups you have in your molecule, whether the reaction actually happened. If you wanted to collect the actual camphor, which is something that we're not going to do in our lab, but if you did want to do that, you would want to decant this solution. Decanting is where you separate things by pouring them carefully. So you'd pour this so that the liquid goes from this container to, say, another beaker, but the solid sodium sulfate does not. And you can use something like a glass stirring rod to hold the solid back. And then once the liquid is in the other container, you can evaporate the liquid away. Probably the easiest way to do that would be gentle heating. You could also just let it sit for a couple hours. Or if you wanted to speed it up without heating it up, you could take a stream of nitrogen. The air that we breathe is 78% nitrogen. So some fume hoods have nozzles to nitrogen gas, which is inert and doesn't react with anything. But when it hits the top of a liquid, it makes it evaporate faster. So that's another way you can evaporate it. Once the ethyl acetate evaporates, there will be a film of solid that's left, and that'll be the camphor. But for us, we're going to stop here. At this point, you have the liquid. Just make sure when you run the IR spectrum, you don't take up any of that anhydrous sodium sulfate that's there as the solid. And so that's the experiment that's a run-through, a sort of guided run-through, walkthrough of the experiment for oxidizing Borneol to camphor.